Hello and welcome to another Arlington High School Math 4 Honors lesson. Today we're going to be doing something a little bit different. We're going to be going through parts of four AP Calculus BC two-dimensional motion problems. Alright, now a couple things about this lesson before we kind of jump into it. Number one, and this is very, very important. For my students, there's no issue. They know exactly what's going on with these problems, and this is for students that are either absent or students who just need to see me do the problems kind of one by one. That being said, for students who might be watching this video that aren't attending Arlington High School and who aren't in Math 4 Honors, these problems are only partial in that we've left out any material that requires the integral or the process of integration to solve the problem. In almost every one of these problems, there's both derivatives and integrals, and Math 4 Honors at Arlington High School only covers differential calculus. We allow AP Calc BC to really pick up where we leave off. So lots of derivatives, lots of parametrics, lots of velocity, speed, and acceleration, but no integration. All right, so when you see a piece missing when we do parts A, B, and D, but we don't have part C, it's because it must have involved an integral. All right, anyway, let's jump right into it. The other thing I wanted to mention about this problem, and actually apologize for, is the quality of the actual problems on the screen. I had to literally scan these problems from a worksheet and then slice and dice them into this presentation, so they look pretty bad. I want to apologize for that. Maybe one of these days I'll actually be able to dig up the original problems online and have a cleaner copy. But for now, we're going to live with it. Let's jump right into number one. A particle moves in the xy plane so that its position at any time between 0 and pi, very important, are given by these two equations, right? Maybe a little bit slightly more complicated one when it comes to the x-coordinate, my apologies for the bell, and kind of an easier one when it comes to the y-coordinate. Now letter A is very, very simple. It just says sketch the path of the particle in the xy plane below. All of the problems that we're going to do are going to be calculator-based, so you have your graphing calculator. So in fact, what I would like you to do right now is pause the video. I am not going to do this, so I'm not going to bring up the Texas Instruments 84. I'm going to have you do that on your own. But take your graphing calculators out, pause the video, and sketch this curve. Use all the information they give you. Things like, they give you T-min, they give you T-max, they really give you X-min and X-max and Y-min and Y-max. So they give you everything. Please pardon the screaming out in the hallways. It's a jungle out there. So right now, pause the video, take maybe 5 minutes, and sketch the path, and don't forget to indicate the direction. All right, let's go through it. Now again, what's kind of nice about this problem is that really, by giving us this grid, the AP has given us everything we need to really get a good window. I think I might do a Y max of 4 personally, but whatever. So we put in our X1 and our Y1 and we graph it, and we get something that looks like this. It starts at the origin, kind of comes up like this, and has a rather almost straight looking kind of appearance like that. Now we want to specify the direction of motion. We're going to do that using arrows. Please don't forget to do that. Often students will, and it's kind of a shame. It's very easy, right? Just watch the direction that gets traced out on your calculator. But simple enough. Probably on an AP problem worth 9 points, that's worth 1 point. So get it right. Letter B. At what time in our interval does x of t attain its minimum value? So I'm looking for the time, I'm looking for t, when x of t is the smallest it's going to be. Now what I'd like you to do is pause the video for a second and try to mark the spot on the graph where x of t hits its minimum. Why don't you do that? Pause the video now. All right, let's do it. I'm going to do it in red just so that it's there. We see it. It's very obvious. I'd say x of t hits its minimum right about there, right? It's getting smaller, 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 greater, greater, greater. Right, I need to actually figure out t. I'm not saying the question mark is t. In fact, it's x. But we have to figure that out. So the question is, what would we know? What would happen at that moment in time to indicate that x of t had attained its minimum? Pause the video again and think about this carefully. Try to write something down. All right, well, To be quite frank, what we're doing is we're changing direction in the x direction. So what we need is we need dx dt, which is the same, if you will, as the velocity in the x direction. We need this to change sign. In fact, what we really need is we need it to look something like this. We need x prime of t, whatever that point in time is, I'll just call it a. We need it to go, x prime of t, to go from negative to positive. We need it to change from moving to the left. We need it to change from moving left to moving right. All right? Well, then we need to figure out dx dt. Let's do it. All right, take a minute. Think about what that is. Pause the video if you need to. All right, let's go through it. I'm going to do this very quickly. We are much past the point in time when we should be talking a lot about derivative rules, but we get something like that, and if I clean it up a little bit by canceling out these 2's, we get a very nice expression. T minus 1 divided by 1 plus t. Now, obviously, I need to figure out where that thing is equal to 0. Okay, now, this is an important point. Okay, we have our calculator right now. We have our calculator. So the key now is that we can solve that equation graphically, but it's a little tricky. So I'm going to write down here, solve graphically. Right? We can solve that graphically. Okay, but we'd have to go back into function mode. Currently we're in parametric mode, but we could solve this graphically by going back into function mode and, strangely enough, putting it in terms of x, and then we could graph this. Now what we have to keep in mind is that that x right here, that x, the one that I just circled, is really t. Now, I know this can be confusing. My students tend to have no problem with it. But I'll solve it graphically, and what I'll find is that t equals, I can't solve it in my head graphically, 1.286. That's what it is, right? We use the 0 command, we use the intersect command, whatever. So that's when it attains its minimum value. What's the position at that particle of time? That's easy, right? We just need to do x of 1.286, and this is going to be terribly messy. But it just is what it is. I mean, there's no real getting around it. I can't even seem to figure out... Oh, I'm sorry. That's not right. Yeah, thanks. Yes, the eraser is selected. It's not 1.286. I apologize. It is actually 0.618. All right? And in fact, if you created this number line... Actually, we already have this number line. If you just did this and put a 0.618 here, this is exactly what you'd find. And now it is as simple, quote unquote, messy, but simple as putting 0.618 into both of these two formulas. You don't need to show that work. I would prefer that my students don't show that work. The AP doesn't really want to see you show the work. All they want to see is this set equal to 0, its solution, and then the coordinate point. All right. It's actually all of this. It's kind of cool. Make sure you can solve that equation graphically. Make sure you understand why that graph in function mode kind of establishes the number line for the x velocity. But that's it. All right, we've got another part of this problem that's going to be on the next side of the sheet, so I'm going to clear this out. Here it goes. All right. Uh-oh. Too many places. So I decided to just restate the original, and in fact I'm gonna redraw the graph really quick so that we have it. Something like that. All right, let's take a look at C. It says, at what time t between 0 and pi? Notice that they've left off the equality now. That's kind of interesting. Or is it? At what time is the particle on the y-axis? Find the speed and the acceleration vector. It's really the acceleration vector, the speed's not a vector, of the particle at this time. Okay, at what time is the particle on the y-axis? What I'd like you to do is pause the video and write down anything you can. If you think you can figure out the time it's on the y-axis, please do so. All right. If not, maybe hold up, but at least you should be able to write something down about this time. Let me circle it, that's why I did the graph. The time at which the object is on the y-axis. So pause the video now and write something down. Okay, this is actually quite tricky because the plain fact is this thing is going to be on the y-axis when the x-coordinates equal to 0. So in fact, I have to solve this equation. And again, I'm going to solve it graphically. I'm going to put myself back in function mode, which I will not do because my students have solved many equations graphically. All right, but I'd put myself in function mode. I would probably use the 0 command. Right? Draw a little graph, find the 0, and what I would find is here's my 1.286. I couldn't read my solutions before, but we would find t equals 1.286. All right, so that's the first part of the problem. Then I have to find the speed and the acceleration vector of the particle at this time. Well, as we should know quite well, the speed is the size of the velocity vector. So the first thing I might want to do is figure out the velocity vector, right? The velocity vector is x prime of t, y prime of t, right? So maybe find those derivatives. I already know x prime of t. It was t minus 1 over 1 plus t. The y prime's pretty easy, right? What is that? 3 cosine of t, right? If I just take the derivative of this guy. All right. So if I want v at 1.286, this is completely acceptable notation because v is a function of t, then it's ugly. You know, I got to plug the numbers in there. It's not interesting. And I get 0.849 as the x component, and I get 0.843 as the y component. Now, of course, the speed, which is what they actually asked me for, is its absolute value, right? And just as a reminder, we would get that by taking the 0.849 and squaring it, the 0.843 and squaring it, taking the square root, a really unremarkable answer of 1.196. We also are asked to find the acceleration vector, right? And the acceleration is best thought as the derivative of the velocity vector. Again, perfectly good notation, no problem there. Maybe a little bit harder to do. What I'd like you to do is think about what the derivative of both of these two things are. Pause the video now and see if you can figure that out. Okay, again, this lesson is not the time for working out basic derivative rules. So I'm just going to find the derivative, state it, and then you should go back and figure out what went wrong if you didn't get it right. But the derivative of that first function is 1 plus 1 over 1 plus t squared. Second one is quite easy, -3 times sine t. What I want is this at t equals 1.286. So I can do the evaluation. Again, ugly, ugly numbers. This is not a surprise. The AP is renowned for not sparing our feelings. But if we evaluate both of these at 1.286, here's our acceleration vector. That's it. That's that whole first AP problem. Granted, there's a little bit missing, but we're not going to worry about that. All right, I'm going to clear out the text. Write down anything you need to. All right, here we go. It's gone. Let's move on. Second AP problem. All right, a particle is moving along a curve in the plane such that it has a position of x of t, y of t at time t, where dx dt, so this is interesting, they're immediately giving us the derivatives. Dx dt is the square root of t to the 4th plus 9, and dy dt is 2e to the t, right? So that's, in case you can't read it, that's 2e to the t plus 5e to the negative t. It's a little bit hard to read there. For all real values of t, at t equals 0, the particle's at the point 4, 1. So we know where it starts. We've got its derivatives. Letter A, should be easy. It says find the speed of the particle and its acceleration vector at t equals 0. I feel like we just did this. So pause the video and see if you can figure that out. All right, let's do it. The numbers here are actually quite nice. And we don't have to do a lot of work, especially for speed, because we already have the components of velocity, right? Velocity is x prime comma y prime at t equals 0, right? We can put 0 into here. 0 to the fourth is 0, plus 9 is 9, square root is 3. Put 0 in here, that would be 1, that would be 1, add them together, and we get 7. There we go. There's the velocity, but of course what we want is the speed. So that's the magnitude of velocity. We'll square them both and add them together, and we'll find a speed of root 58. No units mentioned in the problem. All right, acceleration is the derivative of velocity. Easy enough. Maybe I should just use my calculator on this. We could certainly do it by hand, right? But if it's a calculator problem, and all I need are these values at t equals 0, then I could use that on the TI-84. I could use that numerical derivative command to figure out both of these. Now remember, those would be the derivative of these two functions when t is 0. So that's the way I'm going to do it, right? This is all the work I need to justify, right? This is my justification. How I actually find the derivative, whether I use technology or derivative laws, that's up to the problem itself. If I do, though, use the technology on this, what I would find is that the acceleration in the x direction is 0, and the acceleration in the y direction is -3. Any acceptable vector notation is okay. Letter B, find an equation of the line tangent to the path of the particle at t equals 0. Oh boy, okay, I need the equation of a tangent line. Now, it's a little tricky because at this point you could actually do the equation in two different ways. You could either write it in its Cartesian form, in the typical y minus y1. Let me write this down. Cartesian, right? We could do that in sort of the y minus y1 equals m times x minus x1 form. Or we could write it in parametric form. The AP would accept either one. The one that's way more common is the Cartesian form, so let's do that first. Let's see. What do I know? Well, I got to get the slope and I got to get the points. This is not trivial now. Actually, maybe it is trivial, right? We know what x1 is. It's 4. We know what y1 is. It's 1. How do I know this? Because the problem told me that at t equals 0, I'm at the point 4, 1. So I've got those. I can even do a little bit better. We know that the slope is going to be dy dt divided by dx dt, specifically at t equals 0. But I know what those are. They're 7 and 3. So my slope is 7/3. So it's easy. Y minus 1 equals 7/3 times x minus 4. We've been doing a lot of parametric work lately, so a lot of times students' minds will go immediately to the parametric. Not a great surprise there. If you were going to form the parametric equations, you'd probably write this down. X equals 4, right? That's the coordinate we start at, plus now the x component of the velocity times time. And y, well, that would be 1 plus the y component of velocity times time. And then it would be good to say, hey, let's make time go from -infinity to +infinity. All right, either one is fine. The parametric versus the Cartesian. All right, I'm going to clear all that out, so copy down what you need to. Okay, here it goes. Let's keep going. Problem number 3. Everything else about problem number 2 involved integration, so we weren't doing it. Problem 3, an object moves along a curve in the xy plane, and it has the position, x, y. They told us the x component of the velocity. So remember, dx dt is the velocity in the x direction as a function of time. But they didn't tell us the velocity in the y direction. We don't know what dy dt is. At t equals 2, though, they have given us the position of the object, 1, 8. All right. At t equals 2, they told us that the value of dy dt is -7. They want us to write an equation for the line tangent to the curve at the point x of 2, y of 2. Hey, this is what we just did. Just what we did. So again, let's go Cartesian first. All right, Cartesian, that's going to be y minus y1 equals m times x minus x1. What do we know? Well, again, they gave us the x1, y1. x1 was 1. y1 was 8. That's right here. Yay! The question is, what's the slope? Well, the slope is going to be dy dt divided by dx dt. That's nice. They gave us dy dt. That's -7. And then I'd have to figure out what dx dt is, right? All of this is at t equals 2. That'd be kind of ugly, but I could put 2 in there, and it is not going to be a pretty answer. There's no getting around it. I got to even figure out where I'm at on this. It would be something like 2.3, what is it? 346, etc. Most likely I'd want to kind of crank through that and get -2.983. So my equation now would be y minus 8 equals -2.983 times x minus 1. There's my Cartesian. Again, the parametric setup's not too bad. I don't have a lot of room, I apologize, but it would look something like this. X equals 1 plus 2.346 times t, and y would be 8 minus 7 times t, and then I'd have to have that whole negative infinity is less than t is less than infinity thing. Again, most people are probably going to go with the Cartesian form, which is the form that only contains x and y, but you never know. All right, letter C, no problem. Find the speed of the object at t equals 2. Well, we already know what the velocity vector is, right? It's 2.346 comma -7. So the speed's pretty easy. We'll just find its magnitude. Ugly because we have to square this thing, this one, add them together, take the square root, etc., etc. Not very interesting, but it comes out to be 7.383. Now for the one that's going to cause us to think. There's always standard stuff in these problems, and then there's always parts that cause you to think. So take a look at letter D. It says for t greater than 3. Now, why they gave us that, I don't know. Maybe it's important, maybe it's not. We won't worry for it for a moment. But for t greater than 3, the line tangent to the curve has a slope of 2t plus 1. So I really want you to understand this. For t greater than 3, the tangent line to just the normal xy curve, so if I were to graph xy, I don't know what it looks like, and it certainly doesn't have to be a function, right? But what I know is that the slope of the tangent line is given by 2t plus 1. They ask me to find the acceleration vector of the object at t equals 4. Well, this is definitely a good example of a problem that you have to be willing to play around with. You really do. Now, you definitely want to start by saying, well, how do I find the acceleration vector? Well, I do that by finding the derivative of velocity. So then you might want to ask, well, why can't I just do that? And of course, the reason that you can't just take the derivative of this velocity vector is that although you know this, you don't know this. And it's not 2t plus 1, right? We don't know this. If we knew it, then we'd be good to go. So let's see if we can bring this other piece in that they talked about. Oh, shaking the computer. All right, what do I know? Well, I know that dy dx, right, which is dy dt divided by dx dt, which is dy dt divided by 3 plus cosine of t squared, I know that that must be equal to 2t plus 1, at least for t greater than 3. Now what's beautiful about this is that this then directly tells me that dy dt, watch your parentheses, must be 2t plus 1 times 3 plus cosine of t squared. So that piece of information actually gave me the missing component now in my velocity. Right? The velocity vector is now 3 plus cosine of t squared, and then that ugliness, 2t plus 1 times 3 plus cosine of t squared. Right? The acceleration vector then will be the derivative of the velocity vector. And let me just give you a friendly piece of advice. Do that numerically, right? Do it numerically. There's absolutely no reason to do this in any other way. And in fact, what the AP really wants to see right now is the final answer. That's what they want to see. It's what I want to see. All the justification came from figuring out what dy dt was and stating the fact that the acceleration vector is the derivative of the velocity vector. That's all you have to do. At that point, you can do the numerical derivatives on your calculator. We would get 2.303 and 24.814. Very skewed acceleration vector, almost all vertically. All right, but again, just do that on your calculator. All right, clearing the text out, going on to the last AP problem of the lesson. All right, problem number 4. An object moving along a curve in the xy plane has a position, x of t, y of t, at time t greater than or equal to 0, with those two velocity components given. Okay, so they gave us the velocity in the x direction, right? That's this beast. And they gave us the velocity in the y direction, this beast. They also told us our initial position, so where we are when t is 0. Maybe that's important, maybe it's not. And at t equals 2, the object is at point P with an x-coordinate of 3. All right, I don't think that even has anything to do with the problem because I've omitted the parts that it's actually related to. We're just doing part A and part D. Part A asks us to find the acceleration vector at t equals 2 and the speed at time t equals 2. This has been a recurring theme, hasn't it? Right, over and over and over again, we've been given the velocity vector, or part of the velocity vector, and then we've been asked for the acceleration vector, and we've been asked for the speed at a particular time. I don't like the order that they ask it in this time. I'll be very clear. I do not like the order that they ask it in, because really, the acceleration, which will be the derivative of the velocity, again, we're going to do that simply by using our calculators. The numerical derivative on the calculator, we would do that. Certainly the first one, it would be very easy to take the derivative by hand, and maybe we'll come back to that. But we don't need to do that here, right? In fact, if I take this derivative at t equals 2, the x component is 0, that's convenient, and the y component is negative 1.882. This is the only justification you need. All right, now, the speed's a little bit more obnoxious in a certain sense because we actually have to calculate what the velocity is. In other words, we got to take 2, and we have to plug it into both of these, and what we would find is 12, that's nice, comma 2.833. Of course, finding the speed at this point is going to be no issue because it's going to be its absolute value. So 12 squared plus 2.833 squared. But at the end of the day, that's just arithmetic, and that ends up being 12.330. All right, so it appears like that's something we should be good at before taking the AP exam. My students have plenty of time. All right, let's take a look at letter D. It asks, for what value of t, if any, is the object at rest? Explain your reasoning. I love this problem. So I'd like you to pause the video right now, as much as I want to do the problem. I'd like you to pause the video right now and make an attempt at doing this. And there is a time when the object's at rest, okay? So take a little bit of time. All right, so here's the key, right? If an object is at rest, if it's ever at rest, what that would imply is that dx dt and that's an important word, and dy dt are both equal to 0, and this is key, at the same time, all right? So we could easily have a particle that stops in the x direction, but not in the y direction, right? Oh, hey, look, it's going vertically, but not horizontally. Or something that has stopped in the y direction, but not in the x direction, right? Pure horizontal motion. But if the object's at rest, what that means is that it's not moving. And if it's not moving, the x-coordinate can't be changing over time, and the y-coordinate can't be changing over time. So what we're really doing is we're simultaneously solving these two equations. Now, both of these equations can be solved algebraically. This one's pretty easy. At 0 and 4, this is true. This one, a little bit harder to solve algebraically, but you could. And eventually what you'd find is that t equals 4 is a root. Because of that, what we can say is that t equals 4, both x prime of t and y prime of t are equal to 0. Okay? That's it. I've been skipping over a lot of the algebra and a lot of the calculator techniques because that's not really the focus of these lessons at that point. Those skills are assumed. Okay? If you need work on those skills, this is not the right lesson, obviously. Okay, I'm going to clear out the text. Okay. So that was our first set of AP problems. Hope you got something out of them. Again, I apologize for the messiness of the problem due to the scan. Until next time, though, let me remind you that this has been an Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and until next time,